If you think water is in short supply in California, you should see what's happening in China. Next month, the communist government will turn on the taps at the world's biggest water diversion project.
The mysterious disappearance of vast quantities of fresh water from southern rivers in China has puzzled scientists, hydrologists, and environmental experts for years. According to satellite data and ground observations, billions of tons of fresh water, far beyond what could be accounted for by natural evaporation or standard leakage, have vanished from some of the most important river systems in southern China. This phenomenon is particularly perplexing given the region's critical reliance on these rivers for agriculture, drinking water, and industrial use. What could it be? Well, it turns out that China has just dug massive mountain pits and poured in billion liters of fresh water. The result has been terrifying. Today, we'll tell the entire story. Where has all the water gone? China's southern water system is extraordinarily complex, consisting of an estimated 50,000 rivers of varying sizes and flow capacities. Many of these rivers feed into extensive subterranean water networks and large basins where water is known to resurface in springs, lakes, and reservoirs. Under natural conditions, this interconnected system experiences water loss through evaporation, infiltration, transpiration, and occasional seepage, typically amounting to 5 to 10% of annual river flow, an estimated 150 to 300 billion cubic meters depending on seasonal and regional factors. However, the recent pattern of water loss associated with China's South-North Water Transfer project has far exceeded these natural expectations, with analyses indicating that certain segments of the system are losing up to 15 to 20% of transferred water. The Chinese have measured leakage rates at dam sites, and the numbers exceed 1.5 cubic meters per second, and evaporation losses reach up to 30% in exposed sections of the eastern route. But wait, what is the South-North Water Transfer project? Why is China losing so much fresh water? And what does this mean for the future of the country? This is exactly what we're going to find out today. The Chinese government's comprehensive hydrological surveys, conducted between 2010 and 2020, used advanced tools such as GRACE or gravity recovery, and climate experiment satellite data and ground-penetrating radar to map water flow and storage in southern China, particularly the Yangtze River Basin, Huai River Basin, and the Pearl River Basin, where the majority of water resources are located and tapped for the South-North Water Transfer project. GRACE satellites measure changes in Earth's gravity field, which can indicate shifts in groundwater volumes. The data revealed alarming trends. In some southern provinces like Guangxi, Yunnan, and Guangdong, freshwater levels dropped by as much as 15% over a decade, even in areas with relatively stable rainfall. The magnitude of water loss translated to billions of cubic meters annually, an amount enough to fill hundreds of millions of Olympic-sized swimming pools. These losses could not be explained by conventional evaporation rates, which generally account for only a small percentage of river water depletion. Nor could they be attributed to documented water extraction for agriculture or industry, which, while significant, were insufficient to explain the scale of the anomaly. Further complicating the mystery, extensive hydrological fieldwork found no evidence of major leaks, diversions, or infrastructure failures that would account for the disappearance. Large-scale irrigation projects, dams, and canals have been extensively monitored, with no indications of unauthorized water diversion or infrastructure collapse. Some rumors surfaced about secret mega-construction projects, specifically the possibility of a secret underground city or network of tunnels absorbing or redirecting water. These rumors are fueled by China's history of large subterranean projects, such as the Wuhan Underground City, an abandoned Cold War-era shelter system, and the ambitious South-to-North Water Transfer project, which involved intricate tunnels spanning thousands of kilometers. However, no credible evidence has emerged to confirm that such mega underground structures are responsible for the water loss. Scientific investigations have also explored geological explanations, considering whether the water might be seeping into deep karst formations, underground caverns prevalent in southern China's limestone regions, or if there could be new, undiscovered aquifers absorbing the water. Karst landscapes are known for their unpredictable underground drainage systems, where surface water can quickly vanish into vast subterranean channels. In the karst-rich province of Guangxi, for example, the Li River flows through an intricate system of caves and sinkholes. Yet, hydrologists using isotope tracing techniques, which track water molecules' journey from source to discharge, found that the missing river water was not reappearing anywhere. It was not simply being delayed or stored underground. Interestingly, climate models and rainfall data collected from the China Meteorological Administration indicate that precipitation patterns in southern China have remained fairly stable or even increased in some areas during the period of water loss. This disproves theories that drought or reduced rainfall might explain the freshwater deficit. In fact, the southern monsoon season, which delivers the bulk of annual rainfall, showed no significant weakening. On the technological front, hydrologists have employed advanced remote sensing tools, such as LiDAR or light detection and ranging and synthetic aperture radar or SAR, to create detailed topographic and surface moisture maps. These tools detect changes in soil moisture and water bodies, providing clues about where water might be migrating. Despite these efforts, no anomalous moisture pockets or hidden water reservoirs have been identified. Another avenue explored involves human-induced subterranean activities, such as deep mining and underground construction, which can alter groundwater flow and cause unexpected water absorption or leakage. Southern China is home to extensive coal mining operations and rapidly expanding urban underground infrastructure in cities like Shenzhen and Guangzhou. Some researchers speculate that deep tunnels, mining caverns, or expansive foundations might inadvertently create channels that siphon water away from surface rivers into inaccessible underground voids. However, the scale of such absorption would need to be extraordinarily large and coordinated across multiple provinces to match observed losses, making this explanation less plausible. Intriguingly, some experts suggest that this unexplained disappearance could be the result of a previously unrecognized natural phenomenon, or a combination of multiple subtle factors acting together. For instance, micro-seepage into deep geological faults, enhanced by tectonic activity in the seismically active region of southern China, might be redirecting surface water into deep earth reservoirs. China's southern provinces lie near complex fault lines, and occasional earthquakes could open fissures that act as water sinks. However, seismic monitoring data from the China Earthquake Network Center shows no significant increase in fault activity that correlates with the timeline of the water disappearance. The mystery has also attracted attention from international water security organizations due to its potential implications for global freshwater availability. China's southern rivers are crucial for feeding the Pearl River Delta, one of the world's most densely populated and economically vital regions. A sustained loss of fresh water could threaten agriculture, drinking water supplies, and industrial growth for tens of millions of people. This concern is heightened by China's rapid urbanization, increasing water demand, and the looming threat of climate change stressing water resources worldwide. But now, it appears that we finally have an answer. The mega project revealed through satellite and aerial surveys. In recent years, satellite imagery and aerial surveys have documented substantial infrastructure developments across China's remote mountainous regions, particularly in Sichuan and Yunnan provinces. High-resolution images from commercial satellites, including those operated by Planet Labs and Maxar Technologies, have captured large-scale excavations, the construction of roads, bridges, tunnels, and extensive earthworks. These visual records show significant progress in expanding transportation networks, establishing energy projects, and developing water management systems. The observed activities align with China's long-standing focus on national development through large-scale infrastructure initiatives aimed at reducing regional disparities and promoting economic growth. Among these efforts, one of the most prominent and ambitious undertakings is the South-North Water Transfer Project, or SNWTP, the largest water diversion project in the world. This mega-project was designed to address the severe imbalance in water resources between China's water-rich southern regions and the arid north. The SNWTP's eastern and central routes have collectively transferred approximately 76.5 billion cubic meters of water to northern China. This water supply has benefited more than 185 million people, providing essential resources to 45 large and medium-sized cities, including major urban centers such as Beijing, Tianjin, and Shijiazhuang. The central route of the SNWTP begins at the Danjiangkou Reservoir in Hubei Province. From there, it passes through Henan and Hebei provinces before reaching Beijing and Tianjin, following a course that traverses significant distances across multiple regions. The eastern route, meanwhile, diverts water from the Yangtze River system in Jiangsu province and supplies it to areas such as Shandong and Tianjin. This large-scale water transfer has been critical in alleviating water shortages in the north, especially in the capital region, where water demand has continued to rise in tandem with rapid urbanization and industrial growth. Despite its scale and achievements, the South-North Water Transfer Project has faced several operational challenges. One of the primary technical concerns has been water loss through evaporation. Studies have indicated that the central route of the SNWTP experiences annual evaporative losses of approximately 643 million cubic meters. This figure represents roughly 8.57% of the total volume of water diverted through the aqueduct system. These losses occur due to the long distances the water must travel in open channels and reservoirs, where exposure to the atmosphere allows evaporation to take place, particularly in areas with high temperatures and strong sunlight. In addition to evaporation, siltation has emerged as a significant issue in certain sections of the project. Areas with weak hydrodynamic conditions have been particularly affected, leading to the accumulation of sediments that can obstruct water flow and reduce the efficiency of the system. For instance, Tuancheng Lake, a regulating reservoir located in Beijing, has experienced notable siltation since the central route began operations in 2014. The buildup of sediment in this and other locations necessitates ongoing dredging efforts to maintain the functionality of the water conveyance infrastructure and ensure the uninterrupted flow of water to the intended recipients. Environmental and social impacts of the project have also been documented. One of the most immediate social effects was the large-scale resettlement of communities in the central route's construction zones. At least 330,000 people were relocated to make way for the aqueducts, reservoirs, and supporting facilities required for the project's operation. These resettlements, while managed by government authorities, have had long-term implications for the livelihoods and well-being of the affected populations, raising questions about the social cost of such massive infrastructure endeavors. On the environmental side, concerns have been raised about the ecological consequences of altering natural hydrological patterns. In the source regions, including the middle and lower reaches of the Han River, water diversion has led to decreased monthly flow rates. Reduced flow has, in turn, been linked to the increased occurrence of algal blooms, which can degrade water quality, harm aquatic ecosystems, and pose risks to human health and water usability. These ecological changes highlight the complex trade-offs inherent in large-scale water diversion projects, where the benefits of improved water supply in one region may be offset by environmental stresses in another. To manage and mitigate these challenges, Chinese authorities have implemented a range of strategies. Continuous monitoring of water flow, water quality, and sedimentation rates is conducted using advanced remote sensing technologies and ground-based sampling stations. Environmental assessments are regularly carried out to evaluate the impacts of the project, and engineering solutions are being explored to address specific problems, such as evaporation and siltation. Researchers are developing materials and technologies to reduce evaporative losses in open channels, and sediment management plans are being refined to maintain the capacity of reservoirs and aqueducts. But one has to ask, if the South-North Water Transfer project is so riddled with problems, why did China go for it? The story of the South-North Water Transfer project. China's geography suffers from a fundamental flaw: the uneven distribution of water resources. While southern China, particularly the Yangtze River Basin, has abundant water, northern regions such as Beijing, Tianjin, Hebei, and Shandong face chronic water shortages. The north accounts for over 40% of China's population and nearly 65% of its cultivated land, but it has only about 20% of the country's total water resources. Historically, this imbalance has created challenges for agriculture, industry, and domestic water supply, especially in the North China Plain, which is one of the most important food-producing areas in the country. The idea of transferring water from the Yangtze River in the south to the north was first proposed in the early 1950s by China's then leader, Mao Zedong. In 1952, Mao famously remarked that the south has plenty of water, but the north is dry. If possible, borrowing some water would be good. This vision laid the foundation for what would eventually become the South-North Water Transfer project. However, the technical challenges, economic constraints, and political priorities at the time delayed the project for decades. It wasn't until the late 20th century, when water scarcity in northern China reached critical levels, that the government began to pursue the project seriously. By the 1990s, water shortages in northern cities like Beijing and Tianjin had become severe. Groundwater levels were dropping rapidly due to over-extraction, leading to land subsidence, a reduction in water quality, and an increased risk of ecological degradation. The Hai River, Luan River, and other water sources were no longer sufficient to meet demand. In response to these mounting pressures, the Chinese government approved the SNWTP in 2002 as a national priority project. The goal was to transfer water from the Yangtze River Basin to the arid north, ensuring a reliable supply for urban areas, agriculture, and industry. The project was designed in three major routes: the eastern, central, and western routes. The eastern route, which began construction in 2002 and became operational in 2013, uses the existing Grand Canal system to transfer water from Jiangsu province to areas including Tianjin and Shandong. The central route, the most important and expensive segment, started construction in 2003 and began delivering water in 2014. It diverts water from the Danjiangkou Reservoir in Hubei, traversing Henan and Hebei, before reaching Beijing and Tianjin. The western route, intended to transfer water from the upper Yangtze to the Yellow River Basin, remains in the planning stage due to significant technical, environmental, and political challenges. The decision to build the SNWTP, despite its high costs and environmental concerns, was driven by necessity. Northern China's water crisis threatened food security, economic stability, and public health. The government viewed the project as a long-term solution that could supply over 40 billion cubic meters of water annually to the north. This volume was deemed essential to alleviate water shortages in key cities and industrial hubs. In particular, Beijing, as the national capital, faced an acute water crisis, and the project was seen as a way to ensure water security for this politically and economically vital region. The SNWTP is the largest and most expensive water transfer project in the world. The total cost of the project, as of 2024, has exceeded $80 billion, with over 3,000 kilometers of canals, tunnels, and pipelines constructed across diverse terrains, including plains, hills, and mountains. The central government funded the bulk of the investment, while provincial and municipal governments also contributed, particularly in areas benefiting from the water supply. Environmental and social costs were acknowledged but considered secondary to the strategic goal of addressing the water crisis. The SNWTP was also seen as a way to support economic development in the north. Water scarcity had been a limiting factor for industrial expansion, and by providing a stable water supply, the project aimed to facilitate growth in manufacturing, agriculture, and urbanization. It was considered a key element in China's broader strategy of balancing regional development and reducing the economic gap between the more prosperous south and the resource-constrained north. And now, we come to the problem at hand: water disappearance phenomenon. Between 2019 and 2023, satellite remote sensing data from NASA's Landsat-8 and the European Space Agency's Sentinel-2 missions documented a significant decline in surface water levels across southern China. High-resolution imagery indicates that certain tributaries, which historically maintained consistent flow rates averaging 0.5 to 2 cubic meters per second during dry seasons, have experienced reductions exceeding 70%. In some instances, entire stream segments have dried completely within a single dry season and have not recovered in subsequent wet seasons. These observations contrast with precipitation data from the China Meteorological Administration, which reports stable to slightly above average rainfall in these regions during the same period. Hydrological analyses reveal that water loss is highly spatially selective. Upstream river segments, often originating from mountainous watersheds in the Hengduan and Wuling ranges, continue to exhibit normal flow and seasonal variability. However, further downstream, sometimes within 20 to 50 kilometers, riverbeds transition sharply from healthy flows to dry or near-dry conditions. This pattern is inconsistent with typical hydrological processes such as evapotranspiration, sediment blockage, or agricultural water diversion. Additionally, no significant landslides, earthquakes, or geomorphological disturbances have been recorded in the affected areas that could explain sudden channel obstructions or river rerouting. Investigations by hydrologists from the Chinese Academy of Sciences, Institute of Water Resources, and Hydropower Research have ruled out major dam operations, reservoir withdrawals, or extensive groundwater pumping within the watersheds in question. The Ministry of Water Resources has publicly stated that existing water infrastructure projects in the region operate within standard parameters and cannot explain the sudden downstream water deficits. Groundwater monitoring sensors installed by the China Geological Survey near fault lines and seismic zones intersecting the affected river basins have recorded unusual pressure fluctuations since 2020. These deviations of up to 15 to 20% beyond normal seasonal variability occur along faults such as the Red River Fault Zone and the Xiaojiang Fault, which traverse parts of southern Yunnan and Guangxi. These data points suggest subterranean hydrodynamic disturbances, potentially linked to underground fluid movements or fault zone permeability alterations. Karst topography, characterized by soluble limestone formations and extensive underground drainage networks, is abundant in southern China's mountainous regions, especially in Guangxi's Guilin area and Guizhou's Libo region. The scale and rapidity of the water disappearance surpass typical karst drainage rates, suggesting either a significant structural change underground or artificial manipulation. Some experts hypothesize the opening of new subterranean fractures or caverns acting as water sinks, but direct evidence remains elusive due to restricted access and complex terrain. Hydrological modelling, conducted by the University of Hong Kong's Water Research Centre, utilised tracer dye studies and isotope analysis to track water pathways. Their research, published in the Journal of Hydrology in 2024, confirmed that water from drying tributaries is not reappearing in nearby surface water bodies or conventional groundwater wells. Instead, isotopic signatures indicate deep infiltration into previously unmonitored underground aquifers, possibly tens of meters below the water table. Local communities, dependent on these rivers for irrigation, fisheries, and drinking water, have faced significant socio-economic impacts. In rural Yunnan's mountainous villages, such as Yuanyang and Jinping, agricultural productivity has declined sharply, leading to crop failures and increased migration pressures. Fishermen in Guangxi's Li River Basin reported that catch has declined upwards of 60% since 2020, disrupting traditional livelihoods tied to artisanal fishing and tourism. Local governments have initiated emergency water supply projects, including trucked-in potable water and small-scale reservoir expansions, but these are stopgap measures with limited scope. Despite numerous inquiries by investigative journalists and environmental watchdog groups, official explanations remain vague or non-existent. Statements from provincial water bureaus often cite natural variability or localized water management adjustments without providing detailed data. National media outlets under state control have largely avoided in-depth reporting on the issue, leading to speculation and mistrust among citizens and independent scientists. Efforts by international NGOs like the World Resources Institute to collaborate with Chinese agencies on joint hydrological assessments have encountered bureaucratic delays and data access restrictions. In 2023, the United Nations Environment Programme included the Southern China water disappearance in its Global Environmental Alert System reports, highlighting the potential for widespread ecological disruption and the need for coordinated international research. Remote sensing experts from institutions such as the Jet Propulsion Laboratory have proposed deploying specialized airborne LiDAR and ground-penetrating radar or GPR surveys to map subsurface hydrological features in greater detail. However, political sensitivities and terrain challenges have hampered these initiatives. In 2010, southern China faced one of its most severe droughts in a century, affecting provinces such as Yunnan, Guizhou, and Guangxi. The drought led to water shortages for millions and had substantial impacts on agriculture and ecosystems. Contributing factors included higher than average temperatures and significantly reduced precipitation, conditions associated with El Niño events. Conversely, the region has also experienced extreme flooding events. In April 2024, southeastern China, including areas near Hong Kong, suffered historic floods due to exceptionally heavy rainfall, resulting in the evacuation of over 100,000 people and significant infrastructural damage. The prevalence of karst landscapes in southern China, particularly in provinces like Yunnan and Guangxi, contributes to unique hydrological behaviors. Karst terrains are characterized by soluble rock formations, leading to features such as sinkholes, underground rivers, and caves. These geological structures facilitate rapid infiltration of surface water into subterranean systems, which can result in reduced surface runoff and river flows, especially during dry periods. While northern China has faced significant groundwater depletion, southern regions have also encountered localized groundwater challenges. Excessive groundwater extraction in urban areas has led to land subsidence, increasing the risk of flooding and infrastructural damage. A study published in 2024 reported that nearly half of China's major cities are experiencing moderate to severe subsidence, with 16% sinking over 10 millimeters annually. This subsidence is influenced by declining water tables and the weight of urban infrastructure. Changes in hydrology have adversely affected wetlands and biodiversity in southern China. In areas like Dianqi Lake, there has been a notable decline in indigenous fish species and aquatic plant coverage over the decades. The introduction of non-native species, such as Nile tilapia, has further impacted native aquatic biodiversity in rivers like the Yujiang River. So, where is the water going? Well, there's only one culprit: the hidden cost of the South-North Water Transfer Project. We have already noted that the South-North Water Transfer Project is losing water, and lots of it. But to truly understand the scope of things, as mentioned in the very beginning, take this little bit into context. The project's middle route, which officially began operations in December 2014, stretches over 400 kilometers from the Danjiangkou Reservoir in Hubei province to Beijing and Tianjin. The middle route relies heavily on gravity-fed canals and vast reservoirs to transport water across multiple provinces. However, one of the most glaring issues has been the substantial water loss during transmission, primarily due to evaporation. In its first year of operation alone, the middle route lost an estimated 643 million cubic meters of water, equivalent to approximately 8.57% of the total water diverted. These losses occur mainly because the water travels through open-air canals and expansive reservoirs that are directly exposed to the atmosphere. In arid and semi-arid regions, where evaporation rates can exceed 1,500 to 2,000 millimeters annually, such open systems become highly inefficient. The problem is exacerbated by the need to maintain large surface areas of water to regulate flow and ensure continuous delivery. This further increases the risk of evaporation. The Danjiangkou Reservoir, a crucial component of the middle route, has been significantly expanded to meet the project's demands. The dam's height was raised from 162 meters to 176.6 meters, creating a storage capacity of over 29 billion cubic meters. While this expansion allows for greater water storage and regulation, it has also resulted in the submergence of vast tracts of land, increasing the surface area exposed to evaporation. The western route, still in the planning and feasibility study stages, presents an even more daunting set of challenges. This leg of the SNWTP envisions diverting water from the upper reaches of major rivers, such as the Yangtze, Mekong, and Brahmaputra, which originate in the ecologically sensitive and geologically unstable Tibetan Plateau. The route would require the construction of a network of tunnels and canals through some of the highest and most rugged terrain on Earth, where elevations can exceed 4,000 meters. Essentially, China is digging massive canals through mountains and pouring in billions of liters of fresh water. These areas are prone to earthquakes, landslides, permafrost-related ground instability, and extreme weather conditions, all of which significantly complicate engineering efforts. The construction of the Central Yunnan Water Diversion Project, a related but separate endeavor, illustrates these challenges vividly. That project, which aims to transfer water from the Jinsha River to central Yunnan, involves building over 600 kilometers of tunnels across multiple watersheds and mountain ranges, where geological hazards are a constant threat. Such undertakings require cutting-edge tunneling technologies and massive financial investments, raising concerns about the feasibility, cost, and safety of the western route. Beyond the technical and logistical difficulties, the SNWTP has profound environmental and social implications. Diverting large volumes of water from the Yangtze and its tributaries has already begun to alter the hydrology of southern river systems. This can lead to reduced downstream flows, especially during dry seasons, impacting aquatic ecosystems, wetlands, and estuarine environments that are critical for biodiversity. The reduction in river flows can also affect sediment transport, potentially accelerating erosion and changing the geomorphology of riverbeds. For instance, concerns have been raised about the impact on the Yangtze River Delta, one of China's most fertile and economically important regions, where reduced freshwater inflows may exacerbate saltwater intrusion and threaten agricultural productivity. Environmentalists and scientists have also warned of the unintended consequences of such large-scale water redistribution, including the potential spread of invasive species, changes in water temperature regimes, and alterations in nutrient cycles. Additionally, the alteration of natural water flows can exacerbate issues like soil salinization in areas where diverted water is used for irrigation, further degrading the land's productivity over time. The long-term ecological consequences of the SNWTP remain a subject of ongoing debate, as comprehensive impact assessments are still limited and many effects may only become fully apparent over decades. While the SNWTP addresses the urgent need for water in northern China, where groundwater over-extraction has led to subsidence, depletion of aquifers, and desertification, critics argue that the project's massive scale and associated costs may not represent the most efficient or sustainable solution. Alternative strategies, such as improving agricultural and industrial water use efficiency, implementing wastewater recycling programs, promoting rainwater harvesting, and managing demand through pricing and regulation, could offer more balanced and environmentally sound approaches to China's water crisis. Studies have shown that China's agricultural sector, which consumes over 60% of the country's fresh water, could significantly reduce its water footprint through the adoption of modern irrigation techniques and better crop management practices. Similarly, urban water reuse initiatives and the treatment of wastewater for industrial and agricultural purposes remain underutilized across much of China. Despite all of this, the SNWTP is widely regarded as a shining example of China's innovative approach to addressing critical national issues. It shows the lengths to which nations may go to secure essential resources for their populations, effectively making rivers flow uphill to meet the demands of a changing world. Well, that's it for now. Thanks for watching. Did you like this video? If you did, please consider liking, dropping a comment, and hitting the subscribe button so that you don't miss out on our new uploads. Also, don't miss this video you see on your screen right now. It's truly unbelievable.